Okay, welcome back to your online notes for AP Stats. I want to continue talking about a discrete random variable, and then we'll move into a continuous random variable. There's not as much to talk about with those guys, but continuous random variables is where we're going to be heading for the rest of the year. When we get into our inference procedures, we'll be basing those on continuous random variables. So there's not a lot to talk about with them, but they are pretty important. So anyway, we'll get to those in just a second. So how do you, so we talked about how to calculate the mean last night in the notes, and then how to interpret that. And again, the mean is nothing more than a weighted average. You take each value and multiply it by its weight. Its weight is its probability, and then you add all those up. It's the same, as I mentioned in class, as finding your grade in this class. Your quizzes, tests, and homework scores are weighted differently. So you can find the average of each of those, multiply them by their weight, and add them up, and that becomes your score. Okay? So from last night, the roulette example of placing a corner bet, so basically betting on 4 different numbers, had a mean, a long run mean of negative 0.05, in other words, negative 5 cents, which means that in the long run, you would lose 5 cents if you made that bet, that dollar bet. Well, that's fine. It might be helpful to know each time you place that bet, on average, how much your winnings might deviate from that mean. And so we do that, and since we use the mean as our sort of average or our long run sort of measure of center, then we're going to use the standard deviation to talk about that deviation from the mean. So how do you calculate the variance and standard deviation of a discrete random variable? Well, it's a lot like calculating variance and standard deviation for just a regular variable. If I take a sample of students and measure their height, how do you find the standard deviation? Well, you take each student's height, subtract the mean from it, square that difference, and do that for each student, and then divide it by that n-1 average. Since we're talking about probabilities here in a theoretical model, it's a little bit different. But a lot of things are going to seem similar. So the variance on x is where you start with this, and we know that the standard deviation is just a matter of square rooting the variance. And again, when we start talking about combining these random variables, we're going to understand why we keep talking about variance. So sigma sub x squared is your notation here. Okay. Well, again, what is variance? What is standard deviation measuring? It's measuring an average distance between a value and the mean. So for any discrete random variable, we got to start with the first value on x and subtract the mean from it. And then we're going to square that just like we did before. But instead of dividing by an n-1, our average from last night's notes says we just take the probability assigned to it. We take the weight of this value and multiply it. And that is sort of your way of averaging this. And so we do this for each term. Okay? And we keep going until we get down to the last term. Okay? And we add all those up. And we can sort of shorten this notation by just talking about the sum, the sigma of x sub I minus the mu sub x squared times p sub I, right? Which again just tells us that for each value of your random variable, you're going to subtract that value by the mean, square that difference, and then multiply it by its corresponding probability to kind of get that average, okay? So that's how you do variance. And then, like we said before, for standard deviation, we just square root the variance, okay? How do you interpret standard deviation? Again, it's a lot like the way we interpret standard deviation for just a regular variable. We want to talk about that this gives you an idea of, on average, And I'll do this in terms of rolling the die 3 times. That was the last example that we had for calculating the mean. And so if I roll a die 3 times, over and over and over again, then the mean number of 2s that I would expect to get would be 0.5. So on average, the number of 2s rolled when rolling rolling a die 3 times, it's the same thing. On average, the number of 2s rolled when rolling a die 3 times will differ from the mean by whatever that standard deviation is, right? And so your context comes from whatever your process is. On average, process, or on average, your random variable, whatever you're defining as your random variable, will differ from the mean by whatever your standard deviation is. And so that's where your context comes from, okay? So here we want context in here, and then we want context in here. Otherwise, this is a pretty good template for interpreting any standard deviation, right? So how about going back to our roulette example and calculating standard deviation for each of these guys. So there's 2 different bets we want to consider. So we have this corner bet where you're basically betting $1 on 4 numbers, on any 4 numbers. And when we found the mean here, the mean for your corner bet was, in the long run, you're going to average losing 5 cents for each bet that you place, okay? Red-black has the same mean. So if you just bet on red or you just bet on black, then you're going to have the same mean. These are both going to be negative values. So again, in the long run, or if you place a $1 bet many, many times on either red or black, then you will expect to lose 5 cents for every bet that you make. Okay? That's a distinction we may not have made in the notes last night, that this 5 cents is for every bet that you make. For every $1 bet you make, in the long run, you're going to lose 5 cents. Okay? And since we didn't make that distinction last night, then maybe that 5 cents is a little bit bigger deal. Instead of just having a long run of losing 5 cents. It's 5 cents for each bet that you place. Anyway, they both have the same mean. Let's take a look at how their standard deviations might compare. Now, we need to understand what happens when you place a bet on either red or black. So if we consider that, so X is in terms of betting red or black. So if you bet red, right, so X is the number of red numbers there are, right? And in a roulette table, there are, let's see, 18 red numbers and 18 black numbers and 2 green numbers. So there's 20 non-red, okay? Let's not start here. Sorry. We're going to redefine X. Okay? X is the amount you win in betting red-black. Either red or black. And it doesn't really matter. It's going to be the same. So again, $1 bet. So what are your possible winnings? Well, you could lose $1 from your bet, right? So if you bet on red, then how many times could you lose $1? So what's the probability of losing that $1? Well, again, there's 20 numbers that are not red, and the casino will just take your $1. So it's 20 out of the 38 possible slots. Now, when you bet red or black, it's a 1-to-1 payout. So if you bet $1, you win $1. So your winnings on betting $1 would be $1. You get your $1 back, and then the casino pays you $1. And that's going to happen 18 out of 38 times. Just 18 red numbers. Okay? We needed to kind of go through that real quick so we can calculate our standard deviations. Now, standard deviation for your red-black bet, we can do that first. So the mean is still negative 5 cents. You're going to lose 5 cents every time you place a bet on either red or black every time you make that bet. So the mean is that the variance for that is going to be, all right, the value of your variable, which for the first value is -1 minus a negative 5 cents, square that, and then multiply it by its probability, which is 20 over 38. Then we're going to add to that the other value on x, which is winning $1, minus the negative 0.5 cent mean, square that, and multiply that by its probability, which is 18 over 38. Okay? And when you do all of that work and multiply out, then let's see, then the variance is pretty close to $1. And so when you square root that to get standard deviation, it's going to be pretty close to $1. Okay? Now how about standard deviation for your four-corner bet? Okay? So your four-corner bet is the same process, right? We're going to talk about your variance, which is the same process here. We take the value, and then you look up above in your notes, and you're going to see the first possible amount of winnings is losing that $1, right? Minus your negative 0.5 times its probability, which is 34 out of 38. You add to that the possibility of winning $8, subtracting your negative 5 cents from it, and multiplying by its probability, which is 4 out of 38. Okay? And so you do this math, and then you have to square root. And when you do all of that, and then you square root your variance to get your standard deviation, and you can verify this if you'd like, type that into your calculator, then you're going to get about 96 cents. Okay? So what does that mean? That means that when you place a red bet, if you just bet red all night, right, or in the long run, if you always just bet red in roulette, then on average you're going to lose 5 cents every time you place a bet. The standard deviation on the red bet is $1, which means that on average the amount of winnings will deviate, so the amount of winnings in a red bet will differ from the mean by $1, which means what? Every time you put $1 on the table, you could lose $1.05, right? Or you could win 95 cents. That's what you're likely to do, right? I mean, obviously there are other possibilities out there as far as your long-term winnings. And this is your long-term winnings. How can you have a long-term negative winning of more than $1 when you're placing $1? Well, yeah, I mean, if you place $1 every time, then you're paying out $1. So anyway, these standard deviations are long-run amounts, right? So it's okay that the standard deviation is gives you the possibility of losing more than $1 every time you place a bet, which might be kind of weird. Anyway, how do these two compare? Here's your standard deviations, right? The amount you win or lose may differ from the mean by $1 for a red bet. The amount that you win or lose, will differ from the mean by 96 cents on the four-corner bet. Which one's a little safer bet? Well, that's going to be your four-corner bet, right? Not by a lot, but a little bit. Okay? All right. On page 349, there is an example, or it does walk you through how to use your calculator to find this mean standard deviation. I'll pick out a problem and we'll do that together. Maybe to check your understanding in the book that I asked you to do it using technology. We'll do that in class tomorrow real quick, and I'll show you how that's done. Okay? Because you are going to want to do that. It's a little bit faster, so there's a faster way to do all of this. The next question is, are there any dangers in using your calculator to find the mean and standard deviation of a discrete random variable? And the answer to that is yes, there are some dangers. And what's that danger? What do you need to do for every statistics problem that you may not feel is necessary all the time? And that is showing your work. You still have to show your work. Okay? And again, when we walk through the calculator, let the calculator do your mean and standard deviation for you. I'll talk a little bit more about that and show you exactly how to show your work, especially in situations where you have a lot of different values for your variable. Okay? So anyway, bottom line is, here's how we're going to find our variance and then square root this number to find your standard deviation. And that tells you, on average, how much your random variable might differ from the mean over the long run. Okay? So let's move on and start talking about continuous random variables. Well, a continuous random variable is a random variable still. Okay? And it's still a random variable, but it's a random variable that takes on all possible values in an interval of numbers. So there's no gaps. So there's not going to be any gaps between your values now, right? And again, the example that we used a couple of different examples when we start talking about discrete random variables. I think the one that makes the most sense is the difference between randomly selecting a student here at FC and recording shoe size versus the length of their foot. Okay? Shoe size is going to be very discrete. There are a fixed set of values. So this is going to be your discrete random variable. And there are gaps between them. You either wear a 6 or a 6.5 or a 7 or a 7.5, so on and so forth. The length of someone's foot, while for any continuous random variable, you can turn it into a discrete random variable if you want to. If you're just going to round everybody's foot length to the nearest inch, then it does become a discrete random variable. There'll be gaps between those values. But we know that if we try to measure someone's foot in inches, some people's feet will fall in between two different inch values, right? So someone's foot might be between 9 inches and 10 inches long. If we reduce that or try to make that measurement more accurate into centimeters or millimeters, then we know that people's feet are still going to fall in between different numbers of centimeter length and different millimeter lengths. So we have to consider this as an interval. And so this is what we would call a continuous random variable, right? So the question is, how do we display the distribution of a continuous random variable, right? Well, we can start by looking at the difference between discrete and continuous, right? In a discrete random variable, we showed that distribution by a histogram because there were distinct values, 1, 2, right? But if we're talking about foot length, then we know that people's feet, we can change this to make it make more sense, 9 inches, 10 inches if this is foot length, okay? Well, we know that people's feet might fall in between 9 and 10 inches, and so we would have to introduce an extra bar for, say, 9.5 inches. Okay, thus making our bars, and this is a rough, so don't worry about it so much, but making our bars a little thinner. Okay, but the bars are going to get thinner, right? But hang on, wait a minute. People's feet might fall in between 9 and 9.5. So now I have to introduce another bar at 9.25. And so now I have to make these histogram bars even smaller. right? And I can do the same thing on this side, but you get the point. It could be in between 9 and 9.25 inches, and I'd have to make these bars even smaller. And so the point is these bars keep getting smaller and smaller and smaller and smaller, and to the point where the tips of these bars end up fitting a smooth curve, right? Or it wouldn't go this way, but it would go sort of this way. But it would, the thinner we make those bars, the tops of those bars start to sort of come together and form a smooth curve. Well, that by definition is a density curve. And so how do we display the distribution of a continuous random variable? Well, first off, we can't just list it in a table form like we did with discrete random variables. Discrete random variables, we have very distinct values with gaps, and unless there are an infinite number of those values, we can list them easy enough. But since we're talking about all the possible values in an interval of numbers here, there's an infinite number of values that a continuous random variable can take on, so it makes no sense to show a table form of the distribution. So what we do is we go right to the display, and the display has to be a density curve. Right? Remember that a density curve is a smooth curve, and it's supposed to represent the tops of the bars of a histogram. And as I was just talking about it, those bar histograms get thinner and thinner and thinner because we're introducing more and more possible values for your continuous random variable. Then those tops of those bars will sort of fit this curve. Okay? So density curve. And what we do with density curves before, we talked about finding the area under those density curves as proportion of individuals that fell in certain intervals. Well, remember, in a density curve, it has to be above the x-axis, and the total area under there has to be 1, has to be 100%. Okay? Well, that sounds a whole lot like a probability model and how to make sure it's legitimate. Each probability has to be in between 0 and 1, and the total probability has to be 1, or 100%. So finding the area under the curve is the same thing as finding probability. Okay? I started to make this connection yesterday, or a couple of days ago, I can't remember now, but we make this connection now. So from a normal curve, or any density curve, finding the area under that curve serves two purposes. It's either in a sample, the proportion of individuals that fall in this interval, or in terms of a random process, if I randomly select someone, the probability that they fall in a certain interval. Okay, it serves two purposes. And so density curves do that. There are uniform density curves where you're just using rectangles or triangles to find areas, and we've talked about how to do that before. But our most favorite, I was going to say, but our favorite density curve is the normal density curve, and that's because it's very predictable. We've got our table A that we can use to help us find different values, as well as our calculator, so it becomes a little bit easier to find this area under the curve or this probability, whichever one we're talking about. So an example of a continuous random variable and what we do to find some probabilities. The weights of 3-year-old females closely follow a normal distribution. And again, it's the same as before. You see the word normal. It's what Pavlov's dogs. A bell rings in your head and you go sketch a curve. Right? So sketch a curve. So here's your normal curve. And this is to represent the random variable. Right? And so we're going to define the random variable as the weight of a randomly selected 3-year-old. Okay? So the mean of the weights of all 3-year-old females follows a normal distribution with a mean of 30.7 and a standard deviation of 3.6. So that means that this deviation is going to be at 37.3. This one's going to be at 40.9, and this one's going to be at 44.5. And then we got to subtract from the other side. So this is going to be 27.1, and then 23.5, and then 19.9. Pretty sure. You can check my math on that. Anyway, if we randomly choose one 3-year-old female and call her weight X, so we defined X as the weight of a randomly selected 3-year-old, find the probability that the randomly selected 3-year-old female weighs at least 30 pounds. I'm going to write this in symbolic notation. Okay? Life gets easier if you write it in symbolic notation. Right? So X needs to be, if it says at least 30 pounds, greater than or equal to 30. Okay? That's the probability I want to find. Well, go shade your curve, right? 30 falls right here. And it needs to be at least 30 pounds, so we're going to go 30 or more. Okay? And so now, everything we did in Chapter 2 with normal distributions comes back to us now, right? We could, one, just go use your calculator, use normal CDF, and your lower bound would be 30, because this right here is 30. Your upper bound would be something very, very big, because we want to be all the way out in this tail. Your mean would be 30.7 and your standard deviation 3.6. And that would give you your probability. Okay? Now, shading the curve like this is your work if you want to use a calculator. Don't write this down. Don't write this. Okay? You don't have to write this for your work. Shade your curve and state your value, and that's enough to show your work. Or we can get into Table A. In the Table A, we have to find the z-score. So remember, the z-score is the value that you're concerned about, 30 minus the mean, which is 30.7, divided by the standard deviation. And when you do that, that's z-score is about negative 0.19, at which point you have to go into the table. Remember that the table always gives you area less than, so I need the complement of that. And so this would be 1 minus this value, right? And I'll let you go look that up, okay? But that should be somewhere pretty close to 0.42. And so we're going to be pretty close to 0.58 as the probability of randomly choosing a 3-year-old female and she weighing more than 30 pounds. So as a conclusion here, and this is sort of your 4-step process, this whole thing. So as a conclusion here, the probability of randomly selecting a 3-year-old female and she weighing more than 30 pounds is about, don't forget your about or approximately 58%. Okay? Now it just asks for you to find the probability. This last sort of conclusion probably isn't necessarily what you need to do, but you do need to define your variable, sketch a curve, and then show your work, whether it's through sketching your curve is showing your work for your calculator, or show a z-score calculation and then show how you find the probability from there. Okay? And so that's the difference between finding probabilities with a discrete versus a continuous random variable. In a discrete random variable, we can list out the values and then just add up the probabilities that satisfy whatever it is that we want to know. In other words, if we rounded everyone's weight to the nearest pound, then we could take the probability of this female weighing 30 pounds, 31 pounds, 32 pounds, 33 pounds on up and add all those up. But it's not. We don't do that. They can weigh in between two different pounds, 31 or 32 pounds. They could fall in between there. So this is continuous. And so this is how we would find probabilities using a continuous random variable. And it does involve our normal curve distributions. Okay? Hopefully that made enough sense. That'll conclude the notes for tonight. Homework is attached to the text, so make sure that you see that. You can start on that if you want, or we can have class time tomorrow to get that homework done. Don't forget your test corrections are due tomorrow. Again, if you want, these are optional. And so make sure those are ready to go. All right, have a good night. See you guys tomorrow.